I'm going to talk about two methods, and hopefully you didn't forget everything from day one. And if you remember, I told you about two classes of methods for measuring phase, and one was this thing where you tilt the reference, and we call that off-axis. And in Austria, you call that digital holography. But there are other methods to measure quantitative phase, and the other class would be phase shifting. So I'm going to tell you one for each today. And then Mustafa will tell you applications for SLIM, which is kind of the phase shifting type. Let me acknowledge who contributed the most for this particular presentation, and those are highlighted here. So there's a postdoc who's no longer with us. I mean, he got a new job. Joe has a new job, and these are graduate students. We have a number of enthusiastic undergrads. But also what's important for us as physicists and electrical engineers is to actually work with professional biologists. And I kind of encourage all of you to do that. Because we're not going to fool anyone into turning into, like, convince them that we're professional biologists. So in our particular case, we're happy to have strong collaboration with the neuroscience group, Martha Gillette. We've been working with them for almost 5 years now. Supriya Prasad, cancer cell biology group. But also medical doctors. So Krishna Tangela, who works across the street from Bergman at the Christie Clinic, and he helps us with giving us tissue biopsies and blood, and he tells us everything we need to know about it. And of course, this is a small hospital where you get, in terms of blood and biopsies, you get everything more than you need, but for something more exotic diseases, we don't have them all in Champaign-Urbana. For instance, malaria is not so popular here, thank God. I mean, it's a good thing. But if you want to study malaria or sickle cell disease, we go to Chicago. And we have more recently a connection with Chicago at the pathology, where they have everything. And they have, they're one of the handful of centers in the country for sickle cell disease. So that's also exciting. But we collaborate with people from our own department as well. Steve Bopart should have been highlighted here too, Scott Carney. All right, so here's what I'm going to talk about. First, I'm going to share the background and motivation, kind of repeat a little bit of what I did on Monday. Hopefully you'll remember some of that. And then I'm going to show you two methods, as I mentioned. I'm going to then end with tissue diagnosis and summarize, and then I'm going to let Mustafa tell you some of his exciting things that he's been working on at imaging at the cellular level. All right, so if you remember, this is the problem with imaging live cells. And that is, you don't see them. They are very transparent, they do not absorb, and they do not scatter much. So this is what you would get with a regular bright field microscope, kind of 17th century style microscope. And it took a couple of centuries to go from here to here without adding contrast agents. And this was such a great idea that just by understanding how the optics works, how the light interacts with the specimen, Zernike was able to generate such high contrast image. It was such a great discovery and invention that Zernike received a Nobel Prize in Physics in 1953. But look at this. It took more than 200 years, right? From almost 1600, when the first microscope was reported, to 1930s, okay? 300 years. If you look at the history of the microscope, actually, you can see the progression. The many, many methods that have been developed are actually dealing with contrast more than resolution. And there, as you know, there are two classes of contrast, those that are extrinsic contrast methods, where you add something to the sample, whether it's a fluorophore or dyes or whatever. Nowadays, quantum dots, nanoparticles, and so on. And then there is the second class, where you're trying to use kind of the optics of the tissue itself, endogenous contrast. And obviously my talk is about this second part, endogenous contrast. Phase contrast is about endogenous contrast, but you've seen in Dr. Eliseri's presentation, there are other endogenous contrast mechanisms like endogenous fluorophores and second harmonic signals and so on. So what's the idea with phase contrast? Well, Zernike realized that actually sending, let's say, a plane wave through the cell, there is nothing much happening to the amplitude. Again, that's why you get low contrast image. But there is a lot that happens in the phase, in this wavefront. So the wavefront gets distorted like this. So he understood that, and then he managed to actually couple some of this information from the phase back into the amplitude. That's all. Another method, DIC, differential interference contrast, some of you probably are using it, is using the same idea, get some of this phase and couple it back into the intensity, and I'm gonna, my talk is about that also. These two are very commonly used in pretty much all biology labs. But they have a limitation. They're qualitative. They cannot tell you exactly how much this bending, how this wavefront was distorted quantitatively. Okay? They can only show you, use that information to give you contrast, but you cannot add numbers to it. So basically, for me personally, this has been a challenge and kind of a goal for the past now almost 10 years. I started as a postdoc, I think, in 2002. And the goals kind of have stayed the same from a methods perspective. It's not only to go from a low contrast to high contrast, but actually add numbers onto the image map. So these are phase shifts. Actually, it should be path length shift, technically. And these are nanometers, from 0 to 200 nanometers. And you see, it's the same image, but now it's a quantitative map. So we call this quantitative phase imaging for kind of obvious reasons. And I'm going to tell you two methods and some applications. And then, as I said, Mustafa is going to show you some new results on cell imaging. You can think of this as a combination between phase contrast microscopy, which is great because it doesn't add anything to the cells. The cells are happy. You don't kill them. The visible light is much better than the UV light in terms of how, in terms of not killing the cells. So it's combining this feature with the fact that with ideas from AFM and SEM where you actually get quantitative maps, nanoscale information, but it's the opposite. You cannot image the live cell. Actually, in SEM, you have sometimes to not only be in high vacuum, but actually add a thin layer of metal on top of the cell to increase contrast. So obviously, the cells are dead here, happy here, qualitative information here, quantitative here. So in other words, we want to combine these two and have something quantitative and dynamic. And with nanoscale information, I'm going to show you how. So let's talk about quantitative phase imaging. First of all, phase, if you talk to a biologist, is kind of an abstract thing, right? Obviously, it's something to do with your field, optical field. So how is that biologically relevant? Well, let me put it in the simplest words like this. Imagine that you send this plane wave through the cell, and imagine your cell is homogeneous, of an average refractive index n, sitting in an environment of refractive index n naught. The phase that you measure is going to look like this. This phase shift is going to be proportional to the refractive index contrast, n minus n naught, times the thickness of the cell. So, if you manage to do a very, very good measurement of the phase down to milliradians, that means thousands, 1/1000 of a wavelength, then you have access to sensitivity to thickness changes of down to 1 nanometer. You'll be able to tell whether the cell went up and down by 1 nanometer. So now that becomes something biological. Similarly, you can have, provided now you know the thickness, you can actually measure refractive index changes down to 10 to minus 5 or so. That means the smallest change in the structure of the cell, let's say the concentration of some protein went up very, very slightly, you'll be able to pick that up. Refractive index is pretty much density. So you see how from an purely optical concept, phase, we can actually relate to very important biological structure. One is thickness, the other one is kind of change in density or protein content. Where things are getting really exciting is when you look at fluctuations. So imagine so I image this cell here. This is the nucleus. These are little particles, whatever, organelles, vesicles. So now I'm measuring at this particular point, I measure a blip, the fluctuations in the phase, delta phi. As I mentioned earlier, that could be due to two reasons. One, the thickness of the cell locally changes, goes up and down. But also, and by the way, this term is actually, you can think of it as the membrane kind of undulates, or for whatever reason went up and down. But you can have the second term where actually you can have these particles that move around. So one is out of plane fluctuations of the membrane. The other one is in plane transport of some kind of particles or something that has different refractive index than the surrounding medium. Right? So you see, we can have two classes of applications. But first, let me tell you that both of these fluctuations are analyzed fundamentally in the same way. And it's actually quite interesting that the analysis involves something that we call the dispersion relation. And how many know the dispersion relation associated with light, for instance? How many have heard of dispersion relation? Come on, guys. Don't make me revisit your applications. So a dispersion relation in general is what? Connects spatial fluctuations to temporal fluctuations. Omega to K, or Q. Spatial frequencies to temporal frequencies. The idea is this: if you have something dynamic, whether it's light propagating in some medium, or particles moving around, or membrane fluctuating, what you want to basically find out is, if I decompose, I do a Fourier decomposition, which basically means I'm decomposing my fluctuations in sinusoids. You can imagine then the shorter the wavelength of that sinusoid, let's say on a surface of a lake, of the surface of the cell, the shorter that period, the faster things will tend to move, right? That's kind of the general idea in nature. It happens all the time. So the shorter it is in space, the faster it's going to be in time. But the question is, if I make it twice shorter, is it going to be twice faster, or is it going to be 4 times faster, or 8 times faster? The dispersion relation tells you that relationship. In optics, in vacuum, you have what? K naught equals omega over c. Linear relationship, right? Between the modulus of the wave vector in vacuum and the temporal frequency. So that's simple. But now what happens if you put light in a medium with very strange dispersion, where you have various powers of omega, right? You can have quadratic dispersion, third order, and so on. In that case, it's not obvious. So the dispersion relationship tells you exactly that. This relationship between spatial frequencies and temporal frequencies. So back to our business. If I'm studying membrane fluctuations, the temporal frequency depends on the spatial frequency Q in this manner. So you remember the linear relationship from light in vacuum, totally different phenomenon. Here it means a totally different thing. If I get omega proportional to Q, it's a sign that my membrane is under tension. Right? It's like a soap bubble. If it's Q cubed, that means if I make the spatial frequency 2 times smaller, the temporal frequency will be 8 times smaller. It means that is dominated by bending. So right there, if we're from our data, provided I know how to measure these fluctuations, I'm doing this analysis, spatial temporal frequency analysis. I get a dispersion curve. If I plot omega versus Q, I get it linear. It means one thing. I get the cubical. It means another thing. Similar thing, if I'm looking at the map where stuff is moving around, and again, I'm doing the same thing. It's basically analyzing a movie, X, Y, and time. Now, if omega is proportional to Q, it means exactly the same thing as light propagating in vacuum. It means propagation at the constant velocity. Directed motion. It means the particle in the cell, it's as if it took a bus in the cell and moved at a constant speed. Boom. If it looks quadratic in Q, guess what that means? it means diffusion. Just happens to be that way. Just because the diffusion equation and the wave equation are slightly different. But you can have stranger terms. If you have Q cubed, this typically means that you have now, you don't have a particle diffusing, you have a whole chain diffusing. So you can kind of tell, the higher this power, this exponent, the slower the process. Directed motion, whoop, fast. Diffusion is kind of the drunk person, right? That's diffusion, random walk, slow. Now you take a chain, the diffusion of that thing is going to be even slower than the diffusion of a single particle. So are we clear on kind of the idea? Beyond all these equations, I want you to understand that for a dynamic, for something that changes both in space and time, you need to look at the dispersion relation, because look how simple it gets. You get these polynomials whose exponent tells you exactly what kind of physics you're dealing with, right? Tension, bending, directed transport, or diffusion. So now, really you can do serious biology, provided you know how to measure quantitatively these maps, okay? Whether it's thickness map or transport map. So basically I'm claiming that quantitative phase imaging is great for doing this kind of measurement. So, as I mentioned last time, in my opinion, quantitative phase imaging is growing very fast. If you look in search for keywords on phase measurements, on things like this, you'll get from OSA every week different methods, different papers. Basically, it combines light microscopy, holography, and then I mentioned to you last time there are various types of doing this, and it's something very interesting that actually if you measure quantitative phase, you can extract light scattering information with very, very high sensitivity. I don't have time to talk about all this, but you can find a lot of it here. I tried to summarize it into one book. So instead of giving my students a bunch of different books and papers, now I give them one thing first. So let's review what we did last time. There are two major ways of doing the quantitative phase measurement. One is I have an imaging system. I'm trying to get the phase map of this specimen, illuminated by a plane wave. I make an image here. Let's say this is my microscope. I make an image here. One way is to have a reference overlap to this. So this is a beam splitter. And now I shift the phase of the reference at the average frequency. I provide temporal shifts of the reference, typically in increments of pi over 2 or lambda over 4, quarter wavelengths. The idea being, you see, if I add pi over 2 here, I make this cosine into a sine, another pi over 2 minus cosine, another pi over 2 minus sine, and then you subtract 2 by 2, the cosine terms and the sine terms, take the ratio, and you get the phase of interest uniquely. Another way to do this is to tilt the reference at an angle. So meaning the average k vector of the image. So imagine this imaging has a bunch of k vectors, right? It's not only one plane wave. Because if you had only one frequency, you wouldn't see anything, right? So you have an average k vector of this image, and now the reference comes at a certain angle. So what do you get? You get modulation in space. Essentially, you get fringes across this plane. Turns out we can get the phase that way as well. And these two methods, two approaches, are completely complementary. This one tends to give you better quality image, but this one is faster. So I'm going to tell you one of each kind, and I'll let you judge when to use one or the other. No matter which approach you're using, there is something that I left out here. There is some noise component here, let's call it delta phi, that will come right here. And if you are not careful, it destroys all your measurement. All it takes in terms of phase noise is to have something that goes as 2 pi. In terms of nanometer path lengths, it takes your wavelengths. Visible light, 500 nanometers. And believe me, to have noise of 500 nanometer path length is actually very easy. Naturally, if you try to just put your Michelson interferometer on your optical table, you can float the damn table, you can do many different things. It's still going to shake. It's going to do this. This is a century-old problem, and this is what I'm showing here just as a piece of history. This is the famous Michelson and Morley experiment. How many of you have heard of Michelson and Morley? Okay. So, for those who don't know, how many have heard of Michelson? It's the same Michelson with the Michelson interferometer. This is its implementation here. It's hard to tell which is which. So, Michelson and Morley. Michelson is the first American to win the Nobel Prize, I think, in physics. The Michelson and Morley experiment was an interferometric experiment of historic importance. They were trying to determine the existence of ether, whether the light had different velocities along the different axes with respect to the rotation of the Earth. So how did they do that? Well, they did it interferometrically. If your speed of light has different speeds along different directions, then your phase shifts this way and this way should be different. So believe it or not, people were pretty bold back then. They built a 1.5 ton, I think, or something like that, a ton table on top of a mercury bath. So I don't know about biosafety back then. I don't think this will be allowed today. But so this way you have this humongous thing. You have your optics. You do the measurement this way, and then you simply rotate the table because it's floating. You rotate it and do it again. And as you know, the result of this was that ether was or was not there. So this is the paper that talks about this. But the reason I'm putting this here is that here's what they had to say about the noise. In the first experiment, one of the principal difficulties encountered was the setup's extreme sensitivity to vibration. This was so great that it was impossible to see the interference fringes except at brief intervals when working in the city, even at 2 o'clock in the morning. So now, even in cities, small cities like Urbana, the noise is still there. And actually, I remember when I was an undergrad in Romania, we had to wait doing holography experiments for labs. We had to wait until later in the afternoon when the buses would stop. So noise is actually, it sounds kind of trivial, but it's the biggest problem. And in my opinion, the reason we don't have quantitative phase microscopes everywhere in the biology labs now. I think that's the most important obstacle.
Just a quick comment that's interesting historically. That actually Michelson was Persian. Then they gave him American citizenship when he moved here. But he had done this experiment earlier, like in about 1881. And then when he came here to the United States, he did future experiments with Morley. It was actually here in Chicago, and they did it in a bath of mercury. And they had to stop they had no traffic for several blocks, a huge radius, and they did it with much more precise. But this was actually, they had done it before.
Michelson was Persian?
Yeah.
I had no idea.
Yeah, a lot of people don't know. Many physicists know that. So.
Are you Persian?
No.
See, this is I don't know. Do you know why he got the Nobel Prize for? It wasn't for this. It's like with Einstein, they didn't give it for the controversial. Einstein didn't get it for relativity, as you know, right? Got it for the photoelectric effect. Michelson got it for measuring the ethalon. The meter gave a quantitative kind of measure of the meter in terms of number of wavelengths of a particular line. I forgot what line that was. Cadmium? Ruby, I don't know. So he measured, I think, the first 10 centimeters in the States, and I think he moved to France, right? And he measured the whole meter and he got it there. Anyway, a lot of... I didn't know about the Persian heritage, that's important.
His Wikipedia page says he's born in Prussia, and then it says the first American to receive the Nobel Prize in Physics.
Prussia?
Yeah.
That's not Persia. Okay. Okay, that's totally different. Okay.
But the future experiments here in Chicago, actually.
Okay. All right. Thank you. So let's move on.
Another point is that very important at that time, even physicists don't note this, is that he also measured the velocity of rotation of the Earth from a high mountain with the same type of experiment.
Okay, I believe that. So you remember this table, that there are 4 major features of quantitative phase imaging. And one is acquisition rate, so temporal resolution if you like, how fast you can measure. Transverse resolution means in X and Y in the image, what is that resolution? And that's usually limited by the numerical aperture. Temporal sensitivity, so sitting in one point and measuring over and over again, if I have a blip in the phase, what is that smallest change that I can detect? Spatial sensitivity is the same thing, except that now I'm looking in an image and you give me a step, a phase step in one frame. What is that smallest step that I can detect? And it turns out that off-axis interferometry, or digital holography, or off-axis digital holography, right? Because there is inline digital holography as well. So this takes care of the acquisition rate. Phase shifting takes care of transverse resolution. Phase shifting is just shifting the phase, keeping the frame the same way. The numerical aperture limited resolution is preserved. With off-axis, if you don't make your fringes small enough when you do this, you can lose that diffraction limited resolution. Common path interferometry gives you temporal sensitivity. So making the beams very, very close to one another, such that they see the same noise, that helps you with the temporal sensitivity. And both the techniques that I'm going to show today are common path. Finally, white light, which is the second method, which is SLIM, the one that you've seen in the lab, takes care of spatial sensitivity. Lasers are great, but for imaging are not that great. They give you speckles. So turns out white light helps with that. And I think I mentioned to you last time that you can do combinations of these four. So you can do combinations of off-axis and common path, and off-axis and white light, and whatever. So you can get 6 of those. You can get 4 combinations of 3 of these. And I don't know if I told you this, but there is one that I don't know if it's been published. So if you jump in quickly, you can publish a quick paper. Off-axis, phase shifting, white light. You can do that. And of course, you can one combination with all of them, which I think it hasn't been done either. Probably it's a silly idea, but. So first I'm going to tell you about an off-axis common path method, which we call diffraction phase microscopy, that takes care of fast acquisition rate at the same time, temporal sensitivity. So this is something that we developed at MIT a few years ago. So this was back from '06. And the idea is to use a collimated laser and illuminate the sample in transmission. This is an existing microscope base, and our optics basically starts at the image plane. So you can ignore these 2 lenses here. It's just taking this image and magnifying it a little bit. There is a good reason for that. We can go into details. But as far as understanding the principle, we can start here. At the image plane, right here, again, these are conjugate planes, we're adding a grating. So grating is perfectly overlaid at the image plane. So what does the grating do? I showed you the CD-ROM line. It makes diffraction orders. Out of all diffraction orders, we only care about 2. The 0th order, this one, and the 1st order, this one. So the idea you see right away is that we want to make a very, very tight interferometer. You see it here? 1, 2. And also, the second beam comes at an angle, so you see the idea of off-axis right there, right? So 1 makes the image. These are 2 lenses that replicate this image at the CCD right here. Okay? And the second actually goes here and then comes to the image at an angle. So that acts as reference. But probably you may ask me, hey, which one is the reference, which one is the object? Because they both went through the sample. Remember, they both came from here. Went through the sample. The grating is just splitting them in 2. Right? Did you have that question right away? So that is true. So to fix that, to make turn 1 into a reference, we actually use this lens here. This is basically the Fourier transform. This is where the unscattered light, the transmitted light, is focused at this plane right here. And we add a small pinhole that filters one of the beams, this one. So what happens if I add the pinhole that is very, very small, that's comparable with the diffraction spot at this plane? What happens to that beam? Essentially, you low-pass filter it. the light that goes through the pinhole kind of forgets that it ever been through this sample. It approaches a plane wave after it goes through the second lens, has no structure, is uniform. So that's why this becomes actually a reference. So to summarize, we have an interferometer now that is very, very tight. It goes through the same set of optics as opposed to Michelson interferometer, for instance, where you will have another set of optics like this, and then, okay? This type of microscope, of interferometer is called Mach-Zehnder. And the important thing here is that it goes through the same set of optics. The two beams are actually seeing the same noise. Therefore, if you look at the fringes now, they're fixed. They don't do this that much. Why? Because you can think of this system as basically imaging the grating. These two lenses are an imaging system that basically image the grating. Okay? Imaging is interference. The reason this interference doesn't fluctuate is because these two beams are very close to one another. Okay? So please stop me at any time if something is confusing. But I hope now the principle is kind of clear, right? So I'm going to show you a few examples of how we do this left-hand side of the fluctuations, the membrane fluctuations. And in particular, we looked at red blood cells. They are almost a perfect system for our interferometry and for optics in general. The reason is that they don't have nuclei or other particles, organelles, right? Did you know that? So they're created in the bone marrow, and soon after they're generated, they actually spit out the nucleus. The reason is that they have to be very flexible. So do you know their size, roughly? 7 to 8 micron diameter, and thickness 2 to 3 microns. And they have this particular shape. They have a dimple in the middle. So basically they have excess of area. They have more area than actually they need basically for that volume, right? As you know, the sphere is the perfect packaging kind of shape. They have a lot more area than they need to hold that hemoglobin, but actually that's very useful because this is what allows them to elongate and pass through very, very narrow channels. Believe it or not, in microvasculature, such as in our brain, we have vessels that are half this diameter. So each red blood cell has to squeeze and then bounce back. Squeeze and bounce back. And you may ask, how do we make sure that they don't lose their elasticity? And here's how our body designed, how probably evolution designed the perfect mechanism to test on the elasticity. Our spleen fulfills this function. So once in a while, the cells are forced through our spleen, and the spleen is nothing more but a complicated network of narrow channels, like this. This is an electron microscope that shows beautifully the point. And this is the red blood cell trying to squeeze through those channels. If they make it on the other side, that means they're good to go. They're still deformable, no problem. But if they get stuck somewhere, they lost their elasticity, then they're destroyed by the macrophages. And new ones are coming in. So do you know the life of the red blood cell on average in your blood circulation? 90 days, 100 days. That's it. After that, new ones coming. So basically, elasticity of the red blood cell is what I'm trying to say, is crucial for their function. It's a purely mechanical thing. They have to squeeze, bounce back, and so on and so on. And the spleen is what takes care of it. So their structure is also kind of designed for this. So they have the bilayer, 4 or 5 nanometer bilayer, lipid bilayer, but of course that's kind of like a layer of oil that doesn't bounce back. Doesn't give you shear resistance, right? You can try that with your oil at home. Doesn't hold you back, doesn't have shear resistance, doesn't bounce back. So therefore, underneath the bilayer, there's a network of proteins. Okay, I have these triangles. These are or hexagonal shape, whichever you want to call it. It's like a soccer ball. On the outside you have the leather, and on the inside you have the rubber. Okay, with either one or the other, it's not going to be a good ball, right? So that's the protein network that is called spectrin, is what makes it bounce back. It's what gives the cell shear resistance. So now our data look like this. I kind of skipped over about 3 years of trials and errors and kind of complete frustrations in our lab. And by the way, DPM, the diffraction phase microscope, is the result of many trials and errors. We tried with many different setups first, including trying to measure noisy signal and then canceling it out, either numerically. That didn't work very well. Then we had even an active system. So you'll have a Michelson interferometer and then a mirror that will be active. So we will detect the signal and then we actively kind of cancel that out. So you had to wake up half a day, align the thing, make sure the electronics, the rack of electronics this big would be working, and then get ready, maybe, hopefully, get some images like this. And then finally we realized that all we need to do is to put the damn beams close together, and that's how we came up with the diffraction grating idea. So as you can tell now, what that allowed us to do was kind of exciting. And again, these are a few years old. So we are imaging here at 100 frames a second too. So you can get the phase image for each interferogram. Therefore, the faster the CCD, the faster you can measure. So you're looking at the red blood cell for 10 seconds, 1,000 frames, and the sensitivity is about a nanometer pascal. So some of the first papers are like this. We actually, what's the idea? How is this relating to the elasticity? It's basically, it's like, you know how you can listen to some drums, right? And you can kind of tell which drum it is by the sound it makes, right? So the bass here will be very low frequency, and then what is this called? The main will have a different frequency spectrum. It's kind of the same thing. We are measuring the fluctuations. These are nanometer fluctuations in the red blood cell due to the Brownian motion, due to KBT. And a stiff cell will move less than an elastic cell. That's the whole idea. Now, the theory gets a little bit more complicated, but so in our first paper, we show that actually a normal cell is the most flexible. So the amplitude of those fluctuations are the highest. While when you get these bumpy cells, believe it or not, you will get sometimes these kind of cells in your blood. This is kind of a reversible shape, sometimes. But at some point, these bumps actually are breaking off the cell, meaning some membrane is lost, and therefore the cell becomes more and more spherical. It looks like this. And what we found is that this is actually, the spherical cell is the smallest amplitudes that you get, which makes sense. Meaning that the spheres are not good for circulation. If you have spherical blood cells, they're nice physical objects, round and symmetric, but they're terrible for delivering oxygen through your body, just because there is no room to actually deform a sphere. So we're very excited about this, but we also wanted to do a lot more. So you can see how old this slide is. This actually has been published in 2010. So we measured movies, and now this is a displacement, a snapshot of the displacement, histogram of the displacement. You can actually map at each point of the cell kind of a spring constant. So this is kind of the spring constant, K. And you see it's always stiffer in the middle, meaning that the amplitudes of the dimple are always lower. That's kind of an interesting problem. So again, we wanted to connect to this picture where the cell has to go through the channels of the spleen. And for that, it's supposed to be a movie here. Forget about it. We teamed up with a group of theorists from UCLA. And again, this was published in 2010. So what they designed in terms of a model was kind of the coupling between the bending modes and the compressibility of the cell. So hydrodynamically, you can imagine you have basically liquid inside the cell, liquid outside, and you have these undulations. And these interactions kind of tends to get complex. It's not straightforward. So that's why we went to people who do this for a living. And then with this model, we're actually able to fit our data and get out shear moduli and bending moduli. And we did everything we did before in terms of measurements. Now we're able to extract quantitative numbers. And we even found that, remember the echinocyte, the bumpy cell? if you map these shear moduli, we found that actually going from the normal cell, discocyte, to a spherocyte, obviously the values go up, right, by more than a factor of 2 or 3. And in the middle, in the echinocyte, you get actually a bimodal distribution. It's as if in the echinocyte you have both good membrane and bad membrane, kind of. You can think of it this way. It's as if the underlying protein network is kind of has defects in it. So measuring many cells, you get the bimodal good cells, flexible cells, and stiff cells. While if you look at the spherocytes, you actually get the whole distribution shifted to the stiff bad cells for you. So anyway, these numbers are actually very small. So something that's beyond what you could measure with these macroscopic instruments, right? Like you cannot pull on a spectrum network and measure this way. Then we moved on. We started a collaboration. So this is again when we were at MIT, and I was working with Young Kum Park, whose student is in the room right there. So who's now a faculty at KAIST. So we teamed up with Professor Suresh at MIT, who was back then was the Dean of Engineering. And he managed to squeeze us into his schedule, and we were able to do these measurements with malaria cells that he would grow in their lab. So how many of you know how malaria kind of works? So you get bitten by a mosquito. Then you have this parasite that's traveling in your circulation, looking for a host. Boom, it found it, sticks, somehow gets inside, and then this cell is compromised. Something very interesting happens. The membrane of that cell becomes sticky. Normal cells shouldn't be sticky, otherwise you get terrible circulation. But this one gets stuck here enough to give time to the parasite to hatch. And then break, and you have a number of parasites coming out. And then basically it's downhill from there. You get fever, you get terrible. If you don't get treatment, you can die, basically. So it's kind of incredible that today there are 2 million people a year who die from this disease. We're close to doing some brain transplants in some hospitals, but somehow we cannot fix this. And I think this is kind of terrible. And it affects also mostly children and pregnant women who are most vulnerable to this disease. Do you know the #1 most effective prevention kind of approach for malaria? Huh? Okay, that's, yeah, but it turns out that's not the most effective. Yeah, it's the same you have with the same substance you have in gin and tonic. But that's not the most effective thing. Nets. Bed nets. Bed nets saved millions of lives. Just put the damn net around the beds. That turns out to be the most effective today. Isn't that ridiculous? Yeah, so I think we should be able to do a lot better than this. And basically, I'm going to show you a movie of... if this movie doesn't work, I'm going to be upset. I don't know what happened. So basically, this is a red blood cell that's infected, that has a parasite right here. And if the movie worked, what you would see is that actually the vibrations here kind of die down. So the cell is kind of solid, doesn't move anymore. So basically, this could be a very quick test for kind of diagnosing at the single cell level for malaria. And we think that has a lot of potential. Of course, first we did a lot of more of the basic research. So for instance, we measured various stages in the parasite development, and we saw how actually the stiffness goes up progressively. The longer it stays in the cell, the stiffer it gets. And we're able to track this over 2 orders of magnitude. Both at normal temperature, 37 degrees, and at fever. Okay, so we did all this. And there's no question, this was the easiest experiment ever in terms of seeing differences. When the malaria parasite is inside the cell, you clearly see that actually the cell doesn't move. So all in all, we did a number of publications of red blood cells, kind of quite a number of them, because this diffraction phase microscope allowed us to do fast measurements and also high sensitivity because it was common path. What we wanted to do further was, how about we look at more complicated cells? And actually, my wife doesn't like this kind of calling red blood cells simple because her PhD was in the biochemistry of the red blood cell. But the reality is, you know, the red blood cell lacks a lot of structure that other cells have. And we basically wanted to see whether we can measure this second arm, in other words, mass transport, right? There's no transport in red blood cell, actually, because it's kind of like a hemoglobin soup that's pretty homogeneous. And it turns out the problem with any laser method is that your cell kind of looks like this. And we suffered for this, because of this, for many years. I mean, look at the regular phase contrast image. You see a lot more stuff. This is a neuron, this is a neuron. But I see a lot more stuff in here. Of course, this is kind of quantitative, right? So this red means something that is denser. That's fine. But in terms of how much I can see in the cell, there is no comparison. Phase contrast is better. So basically, that's when I left MIT, when I moved here. And we really wanted to do this, to go preserve this kind of resolution of the phase contrast, but add these numbers, make it quantitative. So we wanted to get rid of speckles. The reason you don't see much in here is the speckles. So this is spatial light interference microscopy. I'm going to tell you the principle, how it works. I'm going to show you a few images of tissues, something that's not cell level, and then I'll let Mustafa tell you the rest. So basically, here's what we do. We get, again, an existing phase contrast microscope, pretty much like in DPM, but now we don't even use another laser source. We use the phase contrast lamp that came with that microscope. Again, our optics starts from the image plane, same idea, but the setup is kind of different now. How many of you know how phase contrast works? How many of you have used the phase contrast? Start with that. There we go. Really? That should be in the application requirement. Okay, so why don't you tell us from KAIST, how does it work? Roughly.
Yeah, roughly. You're separating the scattered and unscattered light, and then you're adding a phase shift to the unscattered light to convert phase into.
Perfect. So let me say it louder. Do you remember how the interference term had an intensity of one beam, intensity of the other beam, and then plus something cosine of the phase difference? Here's the problem. In any image, you can think of the image as an interference phenomenon. The interfering beams are the light that goes through the specimen and deviated, the light that stays as a plane wave, and the light that actually got scattered. The imaging system takes all that light, puts it back together, so you end up at each point in the image is actually, I want you to think of an image as a million interferometers, as made by a million interferometers. The unscattered light, which is a plane wave across all this field of view. And then at each point you get this scattered light that is focused at each pixel here. Okay? They come from everywhere. So the beautiful thing is this image actually has a common reference. It's a million interferometers with a common reference, the unscattered light. You believe me? This idea was fundamental, was put up by Abe back in 1873, who realized that actually an image should be thought of as an interference process, as the result of interference. So Zernike knew this, and then he realized another thing, that the contrast of the image basically should be treated as the contrast of fringes. And for one thing, when you have A plus B plus C cosine of something, if the argument of the cosine is small, meaning you are around 0, your cosine is actually not varying a lot. Do you see what I mean? If I plot the cosine, looks like this. So if my phase is small, I'm looking somewhere here, my cosine doesn't vary a lot. But right? For one thing, the cosine is about 1 minus x squared over 2 as a Taylor expansion, right? So it's quadratic. But the sine, look at this. The sine is actually linear in the origin, right? Sine is actually, sine of x is about x in the origin. You see the difference? This is the difference between no Nobel Prize and Nobel Prize. So what Zernike did was to make this cosine into a sine. And how do you do that? That argument is the phase difference between the light that goes through and the light that got scattered. So if you manage to add a pi over 2 phase shift around this ring is where the unscattered light is focused, then you're done. Okay, so a ring of pi over 2 is what makes phase contrast works. There's another thing. When you have two beams and you do interference, when is your best contrast also? What's another requirement to have the best contrast possible of fringes? Same amplitude, same power. Great. So actually, the ring that you put when you hold on to a phase contrast objective and you look in the light, you'll see that ring that tells you where the unscattered light, where the DC is focused. Actually, that's made of a material that does two things. Does the pi over 2 shift, but also it attenuates the unscattered light. Because usually when you look at something transparent like a live cell, the unscattered light is a lot stronger than the scattered light. So you also attenuate that. In terms of power, you attenuate by a factor of 5 or 6. Okay, so the phase contrast works like this. You have this ring at the back focal plane of the objective. But again, it's fixed. So you get an intensity image that has one unknown, A, plus B, another unknown, plus cosine of another unknown. So clearly, you cannot get the phase out from one single measurement. So what we did was to actually try to gain control over this ring. If I manage to have tunable control over this ring somehow, then I'm all set. So here's what we did. We projected this, we imaged this back focal plane of the objective, that ring thing, onto something like a liquid crystal modulator, an SLM, that allows us to shift the phase controllably from 0 to 2 pi. So we carefully align this ring to a mask on the SLM here, and it looks like that in this plane. For 0 phase shift, this component here acts as a mirror. So the light is reflected back, goes through this lens, and then the CCD records an exact replica of this image plane. That's a regular phase contrast image. Then we add pi over 2, and we measure another image, and another pi over 2, and another image, and another pi over 2, and another image, which is exactly what I hope you did in the lab, right? Somebody? What happened in the lab? What did you do in the lab? Huh? Hmm? You didn't do it? No. You didn't see it? So what did you do for an hour and a half? For an hour and a half?
We looked at past data too. Other images did.
So she didn't do a measurement in real time with you?
No.
Wasn't that in the booklet? But she didn't actually show you how to get an image? No. Wasn't that in the plan?
I saw the actual, it was all set up and we just put stuff on.
We just looked through the microscope to see that.
Right, but when you pushed that, did you see the ring changing? Oh, okay, so some people didn't pay attention. That's a different thing. So when you push that thing, that's what that did. It changed this. Did you see the image changing when you push something?
Yeah.
Whew, all right. So now you take all these 4 images. If you want to see this in action, talk to me. We can set up another one. Now Mustafa is back in town. He'll be happy to accommodate nights and weekends with you. So we combine. We need to move on. The lunch will be here soon. So we combine these 4 images and we end up with this image.
So what I was also online.
Yeah.
It's a great animation. They don't watch. So there's actually a Java thing online. They do the whole base thing online.
Say it again.
Online. Microscopy, the effigy.
Yeah.
Great animation of phase rings. They can do the whole thing online. So it's
Oh, really? Okay. Where should they go? Fiji? Okay. Okay. Oh, the Olympus. Okay. So, problem solved. Right here, if you compare this image with what we had before, you see the progress, right? So now we have all this resolution, we see all these details, and it's also quantitative. So these are nanometers of path length shift. Moving on. You might have another question. I get this question all the time. When you're using white light, right? We got rid of the laser. What's the meaning of that phase shift? Because now you have light from 350 to 750 nanometers. What shift are you talking about? Yeah? Did you have that question? Well, we're talking about the same shift that actually Zernike talked about. And what did he talk about? Actually, if you take this spectrum, it looks like this. If you do the autocorrelation associated with this spectrum, in other words, the Fourier transform of this spectrum, it looks like this. So what do you notice? There is an envelope that is exactly what gives you the longitudinal resolution in OCT. The fact that you have broadband light, it gives you a narrow correlation function. But if you notice, there is actually a very clear sinusoidal modulation that actually is something to do with the mean frequency of this spectrum. So what we're talking about is the phase shift of this. The modulation of the correlation function, of the carrier frequency, if you like. So we're talking about the mean, the shift at the mean frequency, or the more technically, the group delay associated with this broad spectrum. So you see, this modulation is actually very, very well defined, even though you have so many wavelengths. On average, this whole broad spectrum, almost, if you only look at this narrow slicing here, it almost looks like a laser, which is kind of amazing and surprising if you don't know anything about these things. So we're talking about this group delay. That's why Zernike actually, when he did his first ring, he actually put it in green, because the mean frequency turns out to be about 535 in our case. I don't know in his time, but around there. And that pi/2 phase shift is exactly designed for green. And the mean frequency of this white light is in green. So that's the phase shift we're talking about. So first we tested in terms of accuracy. So how good is this thing? If you give me an unknown, let's say a step function, can you measure the height of that with nanometer accuracy, and what is that accuracy? So we actually took a kind of a grating made in Professor John Rogers' group here on campus. There is a carbon film that is stepped like this, and the thickness is about 4 nanometers of each step. So they imaged this with an AFM, we imaged this with SLIM, and we compared the histogram. So the first peaks here correspond to the green, the valleys, and here. And the top is actually the second peak, so the blue regions are the second peak. So you see they agree within a fraction of a nanometer. And we declared, of course, a victory. It turns out that this is the limit for us. The noise, spatial noise, measuring nothing, for instance, gives you some noise like this, which is pretty Gaussian, a perfect Gaussian. And the standard deviation of that is 0.3 nanometers path length. So that's kind of the limit. Compare this with an ugly laser background, and you'll see the difference. This is at least an order of magnitude worse. Laser is too coherent. Now, in terms of stability, so the last two columns in our table, right? Temporal sensitivity, spatial sensitivity. So I told you about the spatial one, 0.3, something like that, nanometers. Temporally, if you measure nothing over and over and over again, the question is, in time, what's the standard deviation of this noise? Turns out it's 10 times better. So this is another Gaussian that's actually an order of magnitude smaller, 0.3 angstrom stability in path length. And the reason is that this is actually the super common interferometer. It's the most common you can get. So the interfering fields here are the light that is focused in these two dots along the ring, and the light that is not, somewhere in here and outside the ring. So this is as close as you can get two beams to interfere. And that's the reason why this is so stable in time. That's the reason when you look at the phase contrast image, it doesn't do this, doesn't fluctuate, or at any other image for that matter. even though it's an interferogram. So I think this is an important concept that if you do interferometry, I want you to remember common path is always the better choice. So SLIM actually covers these three groups here. It's high transverse resolution, high temporal, and high spatial sensitivity. But of course, it's a serial technique. It's a phase shifting technique. For each phase image, we need to acquire 4 intensity images. Therefore, the speed is limited. What you've seen in the lab, actually, with the camera and modulator we have there, can only get 2 to 3 phase images per second, which is good for most cell biology things. But if you want to look at fluctuations in the red blood cell, probably that's not good. So now we have a fast SLIM method in the other lab that you haven't seen that actually goes at 50 hertz, in case anybody needs that. Here are some other features of SLIM. Because we are using that big microscope that has already all the channels of fluorescence, all these other things running through it, they are intrinsically overlaid. You don't need to do anything else to get fluorescence actually already overlaid at the pixel level. So here's an example. Blue and green, 2 channels of fluorescence. This shows you microtubules, and the blue shows you DNA. So for instance, where it stains with green, it tells you that those are my dendrites. And it tells you that's what's left over. This one is an axon. And the red channel is actually the phase. We found that actually if you take the profile over using image J, neuron J, I think, if you profile the dendrites and you compare with the axon, you plot the phase shifts, you actually get that the axon is the smoothest. And this is kind of interesting. So the dendrites accept inputs from other axons from all the cells, right, from many other cells. Axon does not accept anything touching it, connecting to it. Therefore, it's smoother. So the dendrites have these little dots that actually receive inputs from the other cells. So that's why it's twice actually the rougher optically. So we think that these little dots in red, again, red is the SLIM channel, shows you where the synapses form. And this kind of we don't have the synapsin measurements on the same neuron, but it looks qualitatively with another neuron stained for synapses. So these in green dots are the synapses spots. If that's the case, then that would allow us to do kind of measure the dynamics and look at the connections without fluorescence, without kind of affecting the cells. So our microscope, you've seen, it looks kind of like this. I mean, it's a little bit messier than this, but this is the idea. It comes with perfusion chamber, temperature control, humidity, something that Kevin was talking earlier, that it's nice that we have all these accessories that are kind of working now. And I know some of you probably build microscopes from scratch, like I did when I started this. But it turns out that little by little you realize how important it is to actually use something that's already made, where things are working, all these accessories are there. Because then you can actually image things like this. And I'm not going to say too much about cells because Mustafa is going to tell you all about it. But basically you're looking at something that I personally didn't think it would be possible to do so soon. So you look at SLIM imaging of 3 by 3, so 9 tiled megapixel images over a whole week. And as you can see, the cells are happy, multiplying, and so on. We started with a few hundred cells. We ended up with a few thousand cells, while keeping the nanometer stability of the background preserved. So this is kind of, it's possible just because we have all these existing microscopes with all the rings and bells, all the stability, temperature, CO2, and so on, that works. So we have also automation. One thing that we wanted to look at, how about I skip this because Mustafa has a slide on it. So we wanted to understand how the transport, now, if you look at this image, it's a map of density. If you take a movie of it, you can hope to actually try to understand how this density is changing in time and therefore understand transport, which is the second arm of our dispersion relation. So here, for instance, if you zoom into this area and you adjust the colors, you see that there is a lot of signal. The reason you don't see much here is because the colors, the 24 bit, are not enough to kind of capture all the things. Similar here. And DIC, if you know about DIC, actually, that DIC is giving you something proportional to the gradient of the phase. And for that, you need to buy specific optics, specialized optics for DIC. Your objective has to be DIC objective. What we show here is actually if I have the phase, then I take the gradient numerically, I get the same thing. And we play jokes with our biologist collaborators that it's very kind of confusing for them that with the phase contrast microscope, you can get DIC images. So that's kind of interesting. What we found is actually that DIC has an artifact that's well known, and that is called a shadow artifact, a completely non-scientific term, but what it means is that since it's a first order derivative, when you go over an edge, imagine this edge like this. If you take the derivative, you have a high positive slope, and then on this side you have a negative slope. So the intensity is very bright here and very dark here. This is what you see. You can tell that my gradient is along this direction, right? Bright, dark here, bright here. So we thought, hey, if I do a second order derivative, in other words, I take the Laplacian of this is what you're looking at here. Doesn't it look better, easy me? I mean, it looks different, but I kind of like this better because it doesn't have the bright and dark edges. Now, the artifacts come from very bright means curvature this way, very dark means curvature this way. So for one thing, it's isotropic, is not kind of like this, is not directional. So basically, we see a lot of stuff that is not clear in the original image. So Laplacian, like the gradient, is a high-pass filter, and it gives you higher structures in the cell that you couldn't see otherwise. Anyway, what I wanted to show you is how do we do the dispersion analysis on these cells. So you take, this is the movie that you saw. What we do is we take the Fourier transform in x and y and time, and then we calculate the bandwidth of the power spectrum. So we take the Fourier transform also in omega in time, and we take the bandwidth of that, and what we plot is the bandwidth versus qx, qy. Spatial frequency, qx, qy, bandwidth at each point. Why? Because we want to plot what I showed you in the beginning, that bandwidth versus spatial frequency. Do you remember this equation? And what I'm showing you here, it's a kind of an amazing thing to me, that this is almost a universal behavior for all live cells that we've measured so far, with some exceptions, a few exceptions. So it looks like this. At large q, meaning short scales, you get q squared. The meaning of that is diffusion. At low q, you get linear, meaning deterministic transport. So what does this mean? It means that at short scales, the diffusion is actually good enough to move stuff around. But when the cell needs to send something like an organelle or a vesicle from here to here 10 microns away, then diffusion will be too slow. So it's only over large distances that the cell actually is using energy, is sending stuff kind of on purpose. At short scales, meaning below a micron or so, so 2 pi over this gives you the actual scale, so 6 will be 1 micron. Below a micron, diffusion is the most dominant term. So this is a graph that actually you can discuss on it. You can even talk religion about this. So this is kind of the destiny, and this is the free will right here. It's kind of like that. So I think Mustafa is going to show you something along these lines later. But basically, let me tell you one application. I think I'm way over my time, right? Long story short, if we image a slice of tissue that's smaller than the scattering mean free path, it turns out, and that's another kind of exciting result, that you can get and measure the scattering mean free path for those who work with scattering in terms of the phase. Actually, the scattering mean free path relates to the variance of the phase at each position. The anisotropy factor, which is another important scattering parameter, relates to the gradient of the phase. And basically, you can get maps like this. This is a slim image of a whole liver section, radiance here. And we do our little calculation that we call the scattering phase theorem, and you get the scattering mean free path, and you get G. And if you know these two, then basically these have diagnosis values. All the scattering methods meant for diagnosis in vivo have the underlying idea that these two parameters are different for tumor versus normal. The problem is that the reason the progress is slow is that we don't have a good measure to a good method to measure what is normal and what is tumor. We don't have a good way to get the baseline. So we think that having the tissue sliced controllably to thin sections and do a quantitative measurement like this may help in that direction as well. For those who don't know, this is how biopsies are made. There are two ways of sectioning it. So you take the biopsy, it's like a bulk tissue, depends a few millimeter size. You fix it, and then you slice it. If the patient is under surgery, there is no time to do this fixing, and you freeze the tissue, and then you send it to this machine that actually cuts very thin slices, a few micron, 3-4 micron slices. And then both of these go to a pathologist. Legally, from the moment the tissue is extracted from the patient who's under anesthesia in the surgery, legally, the surgeon has to get the results back from the pathology within 20 minutes. So think about it. I witnessed these processes. It's very impressive. So the pathologist gets the call. Then the tissue is frozen, goes to the machine very quickly. The staff brings it to the pathologist. The pathologist puts it under a microscope, looks, and then talks into a microphone up to the surgeon and gives the diagnosis. And then the surgeon decides whether he takes out more tissue or whatever, or closes up the patient, and that's it. The traditional way is to do the fixing and sectioning like this, so the patient goes in and out, and then waits for the result. That may take days. It's a terrible period for that patient, as you can imagine. So from an optical point of view, if you look at the slice of tissue that's 4 microns, it looks like this. It looks like nothing. The same idea. The tissue does not absorb or scatter a lot. It's a phase object. It's transparent. Therefore, what pathology is doing, has been doing for more than 100 years, is actually to stain the tissue somehow, and this is called H&E, the most common staining. And for prostate, there are more specialized stains like this. The reason this is the first used stain, and the most common stain, is because it costs about $10 now. These two specialized stains that are a lot more powerful cost about $500 to $700. So only when there are questions about the $10 one do the pathologists ask for the expensive ones. So all in all, we wanted to have an idea of how slim images will help with unstained tissue. So this is how the H&E stain looks like, and basically this is how the slim tissue looks like. So now from nothing, we actually have a lot of resolution. We see all the stuff in here that matches one by one. We see crystals in breast tissue. These are calcifications that actually don't stain very well in H&E. But since they're crystals, they show very high phases, very high refractive index. So we think there is a lot to be done here. And lately, over the past year or so, we focused on biopsy, on prostate biopsies. So you have to give you a scale, kind of the idea of the size. This is about a centimeter square. And we want to image these with submicron resolution. So what we did was to actually put together 4,000 megapixel images, microscope images of the kind that you saw in the lab. So 80 by 50, and you end up with something like this, and we found something quite remarkable. The doctor gave us the regions of the tumor, the regions of the normal tissue, red and green, and this is a very clear example, very clear kind of tumor, high-grade tumor. And if you look at the refractive index, if you just plot the slim images, you don't see much. But if you plot the variance, so in other words, how much the refractive index is changing from pixel to pixel, you get something like this. So clearly, without knowing any pathology, something is different here than here. It's high value, low value. So obviously, this corresponds to the tumor, and basically, we repeated this over a number of biopsies. So the idea is this. The tumor tissue and the normal tissue are made of the same things, meaning the average refractive index is about the same. But the way the stuff is put together, in other words, in the tumor tissue, you get more disorganized structures, the higher variance, than in here. So you can plot various parameters from the normal and tumor regions, and you get always a good separation between the two from the slim images. But to be taken seriously by pathology, actually, we need to go with thousands of cases. So this is what we've been doing. We now finished imaging 2,000 biopsies that look like this. These are called tissue microarrays. And we're in the process of analyzing all this. But you see how much information we get from the slim images that doesn't require staining. And it's a similar thing in the H&E. We can get all that information by kind of bypassing the stain. So you see the red dots here correspond to nuclei. So high refractive index in our slim images correspond to the black dots in H&E. So we think that we have all we need to do, or all we need to do actually good diagnosis based on unstained tissues. And this is just zooming kind of. We need something the equivalent of Google Earth kind of for our images now. So I'm going to skip through this. This is a high-grade tumor, very bad case. You see all these kind of structures are messed up. Yeah, that's a sign of necrosis. So Shamira, whom you met actually, she actually can do grading from our slim images without looking at H&E. I can't myself, unless it's very obvious. So in summary, quantitative phase imaging can do two kinds of fluctuations. One out-of-plane membrane fluctuations, one in-plane transport, and I showed you just quickly how those work. And we can also do diagnosis and measure scattering parameters. So thank you. And in 5 minutes, Mustafa is going to tell you about single-cell applications, okay? It's going to be a shorter talk, about 30 minutes. Thank you.